Hi, welcome to my channel Electronics Pivot. In today's class, I will be explaining about PN diode, which comes under analog devices. So here I have pre-written few things just to make it easier. First, I'll go into definition part. So diode, it is simply Di plus ODE, that is di means two, and ODE is a short form of electrodes. So what are those two electrodes? One is electrons and other is holes. So these two are the electrodes which we use in PN diode, and these electrons are negative charge carrier and these holes are positive charge carrier. So it is simply that electrons carry negative charge and holes carry positive charge. So only when these carry charges and move, the current will flow. And next is two terminal. So I'll draw the symbol of PN diode and I'll explain what are those two terminals from the symbol. So these are two terminals, A and K. That is, A represents anode, which is positive terminal, and K represents cathode, which is negative terminal. So one end is anode and another end is cathode. Those are the two terminals. And what is this bipolar? So I already told, like, electrons carry negative charge and holes carry positive charge, and only when there is a movement of electrons and holes there is the flow of current. Yes, so that's the meaning of bipolar. For PN diode to operate, there must be electrons and hole movement, and then only the current will start flowing. So electrons and holes both will be the reason for the current flow. Say if any device constitute current only because of electrons or holes, then it is known as unipolar. Here in PN diode, current flows, and that's because of both electrons and holes. Electrons and holes both are the reason for the current flow. Next is unidirection. So current in PN diode flows only in one direction, from anode to cathode, that is from positive terminal to negative terminal, and not in reverse direction, from cathode to anode. Current will not flow. So that's why PN diode is said to be unidirectional. So this is the definition. PN diode is simply two terminal, bipolar and unidirectional device, and I have explained you the definition for the PN diode. So current flows from anode terminal to cathode and not in reverse direction. And coming to explanation of this diode, this triangle indicates the direction of flow of current. So triangle indicates the direction of flow of current from anode to cathode. Okay, and what is this vertical bar? This vertical bar is the current blocking from cathode to anode, that is in reverse direction. Okay, so this triangle triangle mark indicates the flow of current from anode to cathode, and this vertical bar indicates the blockage of current from cathode to anode. That's the representation of the diode. So next is construction part. So PN diode is made up of two layers, P layer and N layer, and P is connected to anode and N layer is connected to cathode. Okay, so there are two terminals and one junction. This is one terminal and this is another terminal, and this is the junction which separates P layer and N layer. Now what is this P layer? P layer is made up of P-type semiconductor and N layer is made up of N-type semiconductor. What is this P-type semiconductor? So here I have mentioned just like a notes. So p-type semiconductor, how we can obtain it is, you just have to add an impurity to pure semiconductor. Say if it is a trivalent impurity, you are adding it to pure semiconductor, then you will get a p-type semiconductor. If the impurity is pentavalent impurity, then you will get a n-type semiconductor. So just you have to add an impurity atom to the pure semiconductor. If the impurity atom, say trivalent impurity like boron or gallium, if you are adding to pure semiconductor germanium or silicon, then you will get a p-type semiconductor. If you are adding a pentavalent impurity like antimony or phosphorus, or sorry, this is arsenic, this is phosphorus or antimony, these are pentavalent impurities. If you are adding to pure semiconductor, that is same germanium or silicon, then you will get a n-type semiconductor. Just you need to add an impurity to pure semiconductor. Based on the impurity, whether it is pentavalent or trivalent, you will get a p-type or n-type semiconductor. Okay, now what is inside p-type? That is p layer and n layer. Inside you will have maximum number of holes and minimum number of electrons. Holes we will indicate as plus and electrons we will indicate as minus. Okay, so here also n layer, it's just opposite. You will have maximum number of electrons and minimum number of holes. It is just opposite, minus, and this is plus. Okay, now as I already told, p layer consists of maximum number of holes and minimum number of electrons, and n layer consists of maximum number of electrons and minimum number of holes. Okay, so let's go into operation. P layer consists of maximum number of holes and minimum number of electrons, and n layer consists of maximum number of electrons and minimum number of holes. Here also anode and cathode. Okay, now what happens is that we all know how magnet works. Magnet works like opposite poles attract and like poles repel. So here also you have same thing. This is the basic principle behind a PN diode. So just remember this: like poles repel and unlike poles attract. This is the basic thing, just do remember this. Okay, so here also maximum, I'll just speak about majority charge carriers. So here majority charge carriers are holes and here it is electron. Both are opposite in charges, so they will try to attract each other. What happens is that the holes from p layer will try to move towards n layer, and electrons from n layer will try to move to p layer. And similarly here holes from n will move to p, and p here electrons will try to move to n. So like this, opposite poles will try to move towards each other. So what happens when these opposite poles are attracting towards each other, they will form a neutral ion at the junction. So I am mentioning neutral ion in this way. Again similarly here leftover electrons, holes, electrons, and here p type has maximum number of holes and minimum number of electrons. So here electron and holes are getting recombined and they are forming the neutral ion. So neutral ion is not a positive particle or a negative particle, it is just neutral. So this is the recombination of electrons and holes. Okay, so here at the junction a neutral ion or recombination of electrons and holes is taking place because opposite poles are getting attracted to each other. Fine. Now there is another thing just we have to consider. We need to think of the weight of holes and electrons. Weight of holes is less because there is more vacancy compared to electrons. So weight of holes is very much less compared to weight of electrons. Since the weight is very much low, the holes can move faster. So holes can move faster compared to electrons. So due to this difference in speed or due to this difference in intensity, what happens is that few of the electrons from N layer will get deposited at P junction and few of the holes from P layer will get deposited at N junction. And again there is a neutral ion which is taking place in the previous step. Okay, so due to the difference in the moment or change in the speed of movement of electrons and holes, the electrons from N layer will get settled at P junction and holes from P layer will get settled at N junction. Now this is called as depletion region. Okay, so depletion region is the electrons, holes and neutral ion. So electrons at P junction and holes at N junction and L neutral ion. This is called as depletion region. First they are trying to recombine and they will recombine at the junction and that is the neutral ion, and due to the speed mismatch you will get electrons at P and layer and electrons at P layer and holes at N layer. This totally is known as depletion region. Okay, now what happens is that, see, there are holes here, right? So these holes again they will try to combine to N layer, but the holes here will start repelling the holes in P layer, so they cannot move to the N layer. These holes will block the holes from P layer, and electrons same way they cannot move towards the P layer for recombination because here there is an electrons which will repel the electrons like poles repel. So these electrons cannot move to P layer because there are electrons at P junction which will repel the electrons. Therefore they also can't move to P layer. Now the recombination is stopped. Once the recombination is stopped, there is a potential that is generated, and that potential is called as barrier potential. For germanium, barrier potential is 0.7 volt, 0.3 volt for silicon, and for germanium it is 0.7 volt. So this barrier potential is actually separating the holes and electrons in further recombination. Now there is no movement of electrons and holes. This is what I explained now is known as no bias condition. No bias means you are not supplying any external voltage. Just combining P layer and N layer, these are the things that is happening. Combination and depletion region, and then a barrier potential. These are happening without any external voltage. So for movement of electrons and holes, what we are doing is we are applying an external voltage that is known as forward bias. What is this forward bias? Say similarly, left over holes, electrons, holes, and this side electrons, left over electrons and holes. Okay, and here electrons, electron hole pair or neutral ion, and then a leftover holes. Okay, so this is the depletion region. Now what is this forward bias? Forward bias is that P layer will be connected to positive of the battery and N layer is connected to negative of the battery. Here in previous steps, why I mentioned it as no bias condition, because we are not applying any external voltage. That's why this operation is known as no bias condition. And now we are applying an external voltage in two ways. One is in forward bias, next in reverse bias. I will explain later. First I will go to forward bias. In forward bias, you are connecting an external voltage, positive of the external voltage to the P layer and negative to the N layer. Okay, now what happens is that, see here also you have to apply the basic principle. The maximum charge carrier is holes, that is positive, and here also it is connected to positive. So like poles repel, therefore the holes will not move in this direction. Holes will not move in this direction, whereas it will try to move in this direction. And here also there is electrons. These electrons will get repelled from the negative of the battery and they will try to move in this direction. Okay, so both are trying to move towards each other. So increasing external voltage, the electrons and holes will acquire a positive charge and they'll try to move towards each other, but still no current will flow because the barrier potential is stopping the recombination once it reaches the barrier potential. That is, say if you are using a pure semiconductor as silicon, which is 0.7 volt. If you are using silicon, then till 0.7 volt no current will flow. Still more, if you are increasing an external voltage greater than 0.7 volt, then current starts flowing. So I'll explain this with a graph. This is a current and this is an external voltage. Okay, so when you are increasing an external voltage till 0.7, no current will flow because the barrier potential is stopping the recombination process, so no current will flow. So once the external voltage reaches 0.7 volt, the current starts flowing. So in forward bias condition, the depletion region will get decreased, yes, until 0.7 volt. When you start increasing till 0.7 volt, no current will flow, and increasing 0.7 volt greater than increasing external voltage greater than 0.7 volt, the current starts flowing rapidly. That's how the forward bias will work. Next we'll go to reverse bias condition. In reverse bias condition, same holes, electrons, here neutral ion, negative gets settled here and positive holes will get settled here. Okay, now here in reverse bias condition, P layer is connected to negative of the battery and N layer is connected to positive of the battery. Now what happens is that the holes here will get attracted towards the negative of the battery because opposite poles attract, right? So it will move towards the negative of the battery, and this side also the electrons in N layer will move towards the positive of the battery because opposite poles attract each other. Okay, now the majority charge carriers in P layer will move towards the battery and not inside the PN diode. So all the majority charge carriers are moving out of the device, that is are moving towards the battery. Therefore there is no current that flows inside the depletion region. Because of these minority charge carriers, a small amount of current will flow, that is known as leakage current. See here you are applying a negative voltage, yes. This in reverse bias condition you will apply a negative voltage, so small amount of current starts flowing, that is leakage current. Here when you apply a negative voltage, this depletion region's width will get increased. And increasing, so here external voltage you are increasing, so when you increase the external voltage, electrons starts moving towards the battery, and hence the depletion region will starts increasing, and still more increasing the external voltage. These holes and electrons will for them it will become very difficult to cross the depletion region because it is getting increased. So what happens is that from the voltage they will try to acquire a large amount of energy, and they will try to move. What happens is that when they acquire the large amount of energy to break the depletion region and move, this depletion region will get overheated, and it will break. Starting when you increase a negative voltage, this depletion region will start increasing, and this positive and electrons and holes will acquire energy from this voltage. But still more increase the negative voltage, they will try to move at the faster speed, and it will damage the depletion region, and hence there is a junction breakdown, which is also called as avalanche breakdown. So once this avalanche breakdown happens, the current will flow at a faster rate. So here this is the current, this is the external voltage, that is negative voltage, and this is the leakage current. This leakage current is due to minority charge carriers. So increasing this negative voltage, the depletion region will break and a large amount of current will flow. So that's everything about the reaction. This is the first three steps are no bias condition. Next is forward bias condition, where you will apply a forward positive voltage till 0.7, no current will flow. Once it reaches, external voltage reaches 0.7, large amount of current will flow. And in reverse bias condition, increasing negative voltage, depletion region will increase, so it will become difficult for the electrons and holes to combine. So they will take an more energy from this negative voltage, and they will try to move, and still more increasing negative voltage, this depletion region will overheat, and the electrons and holes will move at the faster speed, thus damaging the depletion region or the junction, which is known as avalanche breakdown. If you see, the current flows from positive of the battery to the negative of the battery in this direction, that is current is from moving from P to N. Okay, that's the direction of current. But in reverse bias direction there is no current flow. That's why in symbol I have represented like the current flows from positive of the battery to the negative of the battery, or anode to cathode in the forward bias condition. In reverse bias condition, there is no current flow, because once a large amount of current is flowing and it damages the depletion region, and hence this diode cannot be used in the reverse bias condition, and it is only used for the forward bias condition. Thank you. Hope everyone understood. If you have any doubts, please let me know.